Let's now look and see how the Sackur Tetrode equation helps resolve the Gibbs paradox. And just recall, we'll use the Sackur Tetrode equation in the form here. And I'll use it to calculate the change in entropy for the mixing of an ideal gas. I'll look at the two cases pretty much the same as before, just to verify that it gives us the usual results, at least in one of the cases. Let's first look at the case where I have two ideal gases. They're same number of particles. I've got a partition in between, an impenetrable partition. Both sides, the left and the right, have volume V, and they're both at the same temperature. The only difference is on the left I've got the particles, the ideal gas has a mass, particles have m sub a, and ideal gas has m sub b on the right hand side. And then I remove the partition. This is the initial state over here with the partition in place. I remove it to get to the final state and allow these things to mix. And what we find is that we've got, still have n number of particles of mass ma, n number of particles of mass m sub b, but now they're free to roam, both of them are free to roam over the full 2v, which is the initial 2 times the volume is over here. And since they were at equilibrium temperature-wise, well, it's still at temperature. And so I just used the Sackur Tetrode equation to compute the entropy before and after. For molecule A, the Sackur Tetrode equation gives us this. It's confined to volume V, and that's for molecule with mass Ma. And for Mb, it likewise is enclosed in volume V, and n of them in the Sackur Tetrode equation gives this. So these terms are very, very similar, but I have one for Ma and one for Mb. And then the final is not much different. I still have mass A, but that's the x's here, but they're free to roam over the entire volume, and so the final is the volume in the Sackur Tetrode equation is 2 times the original volume, and an in here. And then likewise for molecule B, that's the circle ones, the mass is Mb, Ma, and it likewise is able to roam over the full 2V, that's the final volume. And then I just take the difference of those two. So there's the final minus the initial. I write it in this form, and then I group these two together. And they have the same factor nkb out front, and I've got the logarithm of a difference, and so I can simply divide this argument here by this one for the first term, and then the second term is similar. I group the two with the masses the same so that I get cancellation. So this log minus this one can be written as this, and I get lots of cancellation. Everything cancels except for this factor of 2, and likewise this one minus this one can be written as the ratio of those two arguments. And again, mass B's, so I get lots of cancellation. I get natural log 2. And we get kind of a reassuring change in entropy in this case is just this 2 natural log 2 of nkb, which is same as the thermodynamic result would have given for this. And that, I think, is somewhat reassuring. But now let's look at the case where Ma equals Mb equals M. And now you've got this arrangement. You've got N. You have N particles on both sides, the same particles, so they have the same mass M. They have the volume on the left and the volume on the right at equal temperature and mass M. That's the initial state, and then it goes over to the mixing state. And now I've got two N particles in the final, and they're able to roam over twice the volume once I break the partition or remove the partition between the two. And so just like before, we have our initial result up here, except the only difference is that MA and MB are the same M, and they're able to roam over all of it. So really I get the same term in both cases, and that's what I've written here. I get a factor of 2. They're confined to volume B, and I've got N particles. Just picked up that factor of 2. And then the final is now a little bit different, because now I have the Sackur Tetrode equation. I have 2N particles, 2N here, 2N here, but they have the volume as twice the volume. And so the final entropy of the system is just this expression, 2N, 2V, 2V, because it again gets to roam. I have 2N particles roaming over that whole volume 2V. And again, you get some cancellation here. The 2's go out. And then I just subtract SI from SF. But if you look at those two, they're identical. The final is 2N KB natural log V over N. And the original, the initial one was, due to the identical particles, was the same. And so you find that in this case, delta S is indeed reversible. There's no change in entropy between those two because I could slide a partition and get exactly the same system. So in that sense, the Gibbs paradox is resolved by the Sackur-Tetrode equation and the quantum theory. And in 1912, when this was first published, it was taken as a strong confirmation of the ideas that were being developed on the quantum theory of matter. As I said, probably Nobel Prize winning type work, but neither Sackur or Tetrode got the Nobel Prize. They both died shortly afterwards. Hugo Tetrode, the physicist, actually contracted tuberculosis, I believe it was, and died shortly after publication, within 10 years or so, I think, of publication. And then, so he died of tuberculosis. Easily curable today, but in those days, in early 1900s, was not curable. They didn't have the antibiotics to do it. And then, likewise for Otto Sackur, he actually went to work for Faber Chemical and died, I think, within a couple of years of this paper. Died in an explosion mixing up the two chemicals. Probably working on explosives for Faber Chemical, but died in a chemistry lab explosion experiment. So I guess he should have kept to theoretical statistical mechanics and quantum chemistry.